I'm going to review the material in Unit 15, which has to do with reduction of state tables and state assignment. We'll start by talking about equivalent states, because in order to reduce state tables, we have to eliminate equivalent states. So in general, the idea of state equivalence is if we put an input sequence in and look at the output sequences, we can't tell the states apart so that they're equivalent. Let's consider network N1 and start it in state P, and network N2 and start it in state Q. Or these could be copies of the same network. I'm going to put some input sequence X into both networks. The under bar here indicates a sequence rather than a single input. I'm going to look at the output sequences. Z1, which is a function of the starting state P and the input sequence X, and Z2, which is a function of the starting state Q and the input sequence X. And suppose those are the same. Now let's reset the networks to P and Q and put in another sequence. And look at the outputs, and supposing those are the same. And then we reset it again and put in a different sequence and look at the outputs, and supposing they're the same again. And supposing we find for all possible input sequences, the output sequences match. We can't tell the states apart, and we see they're equivalent. This leads to the definition that state P is equivalent to state Q if and only if for every input sequence X, the output sequences are the same. Now, although that's a good definition, in practice it would be very hard to test the states this way, because we'd have to put in all possible sequences, which would include short sequences and very long sequences, in fact, infinite sequences, and that's just not practical. So usually when we test for state equivalence, we make use of the state equivalence theorem. Now, when applying the state equivalence theorem, we're only using one input at a time rather than a sequence. And here's our same two networks, N1 and N2, and our same two states, P and Q. So we put in a single input X, and we look at the output, Z1, which depends on P and X, and the output here, Z2, which depends on Q and X. We also look at the next states, and again, the next state in the first network depends on P and X, and the next state in the second network depends on Q and X. So we'll say that P is equivalent to Q if and only if, for every single input X, the outputs are the same and the next states are equivalent. So this is different than the definition. In the definition, we didn't look at the next states. We only looked at the outputs, but we had to put in input sequences. Here we're only putting in one input at a time, and we're looking at the single output, and we're also looking at the next state. So when trying to find equivalent states, we're going to make use of the theorem rather than the definition. Next, I'm going to apply the state equivalence theorem to reducing a state table. Here is a state table with 7 states. And the first thing I'm going to do is look to see if there's any identical rows. So here we have rows A, B, and E all have the same output, but they have different next states. Then we have rows C, D, F, and G all have the same output. And looking at the next states, we see that C and G both have EF as next states. So the outputs are the same and the next states are the same. So we can immediately conclude that C is equivalent to G, which means we can eliminate state G and replace G with the equivalent state C. And then we should look at the table again to see if there are any other identical rows and eliminate them. Having done that, we'll then make a pair chart and test for equivalent pairs of states. So first we'll construct a grid which has one empty square here for each pair of states. And I'll label this at the bottom, starting with the first state here, A, B, C, D, E, and then starting with B at the top, B, C, D, E, F. So there's one square for each pair of states. And then I'll look at the state table, and states A and B have the same outputs. And the next states are AB and DF. So I'm going to fill in the chart with AB and DF. And what this means, that state A is equivalent to B if and only if A is equivalent to B and D is equivalent to F. And later we'll check to see if D is equivalent to F. Now, next pair is A and C. So looking at A and C, the outputs are different. So I'll put an X there. Next pair is A and D. Again, the outputs are different. I'll put an X there to indicate the states are not equivalent because the outputs are different. What about A and E? A and E have the same outputs. What about next states? Well, here we have next state is B, is the same. Here we have next state C and F. So we conclude that A is equivalent to E if and only if C is equivalent to F. What about A and F? A and F have different outputs, so they're not equivalent. B and C have different outputs, not equivalent. B and D have different outputs, not equivalent. B and E have the same outputs, and for x equals 0, the next states are AB, x equal 1, the next states are CD. So I'll write AB here and CD. So B is equivalent to E if and only if A is equivalent to B and C is equivalent to D. What about B and F? Different outputs, not equivalent. C and D, same outputs. The implied pairs are BE and BF. BE and BF. What about C and E? C and E have different outputs. What about C and F? C and F have the same outputs, and the next states would be AE and CF. D and E. D and E have different outputs. D and F have the same outputs. The implied pairs are AB and BC. What about E and F? Different outputs. So after the first pass, I've marked X in all the squares which correspond to states which are not equivalent because the outputs are different. Then we have to go on from there. And here is a copy of the chart we just filled in, with the X's indicating state pairs which are not equivalent. And I'm going to make a second pass through the chart and see if I can cross out some additional states. Here, A and B being equivalent depends on D and F. And D and F doesn't have an X, so we'll go on. Here, A and E being equivalent depends on C and F. And C and F doesn't have an X, so we'll go on. Here we have AB and CD, and neither AB or CD is crossed out. Here we have BE and BF. BE is not crossed out, but BF is. Since B is not equivalent to F, this implies that we can put an X here, meaning C is not equivalent to D. And then we have AE and CF. AE, again, does not have an X, and neither does CF. Then we have BC. BC has an X, so we can cross that out. So that's the second pass. And since we eliminated some states during the second pass, we have to do a third pass. We crossed out CD, and CD appears here. So we cross out this square. And since we crossed out that square, which is BE, there's no BEs, but we have crossed out DF here, and there's a DF here, so we cross that out. And we just crossed out AB, and that doesn't appear anywhere, so we're done. So we eliminated all states which are not equivalent. The remaining pairs which are not X'd out are equivalent pairs. So we have A and E, the coordinates of this square. A is equivalent to E, and then here we have C and F. So C is equivalent to F. So we can now reduce the state table since we found these equivalent states. So I'm going to eliminate F and replace F wherever it appears with the equivalent state C. And A is equivalent to E. So I can eliminate E. And wherever E appears, I'll replace it with the equivalent state A. So now I've reduced the state table to 4 states, which is a minimum number of rows. And once we've completed reducing the table, we can then go ahead and derive the flip-flop input equations. And because we have fewer states in the table, this means we'll have fewer flip-flops. And it also means that we'll have less logic. After the state table has been reduced, the next step is to make a state assignment. The object of making a state assignment is to reduce the amount of logic required. So we're going to work out this example here to show equivalent state assignments. Here is a table with 6 states, and we want to assign some combination of flip-flop states to correspond to these 6 states. So we have 3 flip-flops required, Q1, Q2, and Q3. And here is one possible assignment. And here is a second assignment. And these are related. If you look at the first column here, we have 0, 1, 1, 0, 0, 1. And the second column here is the same, 0, 1, 1, 0, 0, 1. And the second column here, 0, 1, 0, 1, 1, 0, is the same as the first column here, 0, 1, 0, 1, 1, 0. So these state assignments are the same, except Q1 and Q2 have been interchanged. If you look at the last column here, 0, 0, 1, 1, 0, 0, and complement it, we get 1, 1, 0, 0, 1, 1. So Q3 differs from here to here in that we've complemented Q3. So these operations in general will not affect the amount of logic required to realize the state table. So we say that these are equivalent assignments. So to illustrate this, we're going to first derive some JK equations using the first assignment, and then we'll make use of the equivalence to get the JK for the second assignment. So wherever we have Q1 here, we'll replace it with Q2, and wherever we have, and vice versa, wherever we have Q3, we'll replace it with its complement to go from assignment 1 to assignment 2. But first, let's derive JK flip-flops for assignment number 1. I'll start by filling in the transition table. Here's the state assignment I'm using for states A through F. And wherever I have state C, I replace that with 101. So the next state here is 101, and the next state here is 10. For F now is 100. And for A is 000. And for C, it's 101. And for F, it's 100. And for D, it's 011. And for E, it's 010. So here we have B and E. B is 110, and E is 010. Here we have D and C. D is 011, and C is 101. Here we have B and A. B is 110, and A is 000. So that completes the transition table for this state assignment. Next, I'll plot the Carnot maps for the next states. So I'm going to work with the table up here, and for x equals 0, q1, q2, q3, 0, 0, 0, that's this square on the map. And the next states for q1, q2, and q3 are 101 respectively. So I'll fill in 101. Now when x is equal to 1 and q1, q2, q3 is 0, 0, 0, that's this square here. And the next states are 1, 0, 0 respectively. Fill in 1, 0, 0. All right. For x equals 0 and q1, q2, q3, 1, 1, 0, that's square number 6 on the map, 0, 1, 1, 0. And the next states here are 0, 0, 0. 0, 0, 0. And the next states here, when x is equal to 1, that's this square here, 1, 1, 1, 0. And the next states are 101, 101. Then, for the next row, x equals 0, that's 0, 1, 0, 1. Square 5 on the map is this square. And the next states here would be 1, 0, 0. And when x is equal to 1, that's square 1, 1, 0, 1 on the map, square 13 here. And the next states are 0, 1, 1. All right, with row 0, 1, 1 here, and x equals 0, that would be 0, 0, 1, 1, square 3 here. And the next states for square 3 would be 1, 1, 0. And when x is equal to 1, that's this square here. And the next states are 0, 1, 0. And then in square 2, and x is 0. So that's 0, 0, 1, 0 here. Square 2, we fill in 0, 1, 1. And when x is equal to 1, that's this square here, 1, 0, 1, 0. And the next states are 1, 0, 1. Finally, for the last row here, x is 0, 1, 0, 0. That's square 4. The next states are 1, 1, 0, 1, 1, 0. When x is equal to 1, that's square 1, 1, 0, 0, this square. And the next states are 0, 0, 0. Now, the remaining squares correspond to unused states, so we don't care what the next state is in those cases. So I can fill in don't cares on the next state maps. Now we'll go ahead and derive flip-flop input equations for each of the maps. First for flip-flop 1, and I'm going to use a JK flip-flop here. So keep in mind here that we're going to split the map into two halves, one where Q1 is equal to 0. That's these columns here. Q1 equals 0. And the other half of the map where Q1 is equal to 1. Now for the JK flip-flop, remember when Q is equal to 0, whenever the next state is 1, J must be 1. So J is equal to the next state, Q plus. In this case, this is Q1 and Q1 plus. And correspondingly, K is a don't care, and since we're using the shortcut method, we won't even plot a map with those don't cares on. So we're looking at the Q equals 0 half of the map, and J1 is Q1 plus. So the first and last columns here, we're going to circle the 1s here. So this one and this one are adjacent, and that combines with the don't care, so we can make a loop there. And then we have this one here combines with that don't care, nothing, just a 0 over there. And this one here will combine with the top one. So we've got 3 terms there for JQ1. The first term here, remember we're going to be eliminating Q1 here, setting it equal to 0 or 1. So what's left here, we've eliminated X, and going for the top 2 rows, we eliminate Q3 and just leave Q2 prime. Plus, the next term here, this loop here is X prime Q3, and then this loop here would be X Q3 prime. All right, then if we look at the Q equals 1 half of the map, we find that K is equal to the complement of Q1 plus, K1. So I'm going to read the zeros off of this half of the map. So here's a 0 and a don't care, and here's a pair of zeros. So I have 2 terms. This term here is X prime Q2. And the next term here is X Q2 prime. So that takes care of flip-flop number 1. Flip-flop number 2, I'm going to split my map in half again for Q2 equals 0 and Q2 equals 1. And again, to get J for Q2, I'm going to circle 1s on the Q2 equals 0 half, which is this one here and this pair here. And I'm going to eliminate Q2. So this term is X prime Q1 Q3 prime, X prime Q1 Q3 prime. This term here is X Q3. All right, and then to get K, I'm going to circle zeros on the Q2 equal 1 half of the map. So I can circle this group here, this pair here, and end up with, I've eliminated X, so I just have Q1 here, and I've eliminated Q2. So that's simply Q1. And over here I have X Q2 prime. Excuse me, X Q3 prime. So that's the JK equations for flip-flop number 2. For flip-flop number 3, we split the map here. Q3 equals 0 in the top and bottom rows, and Q3 equals 1 here. So again, looping the 1's to get J, we're going to have this one here and that one there, and this pair of 1's here. And we've eliminated Q3 by setting it to 0 or 1. So what's left here is x prime Q1 prime, and we've eliminated Q2 from top to bottom. All right, and this loop then would be x Q2. And for k's, we're going to circle the zeros on the other half of the map. So we've got this group here and this group here. So that gives us x prime for the first loop. And for the row here, we have Q2. So we've derived the equations here, and there may be another way to loop this, but this should suffice. We could have looped this pair here also, which would have given us a different solution, x prime plus Q1 prime. Either one is fine. So now, we're going to apply the equivalent assignments here to show that we'd end up with the same type of equations for the j's and k's. So here's the assignment we started with, and we derived these equations. Now, for assignment number 2, remember Q1 is replaced with Q2, and Q2 is replaced with Q1, and Q3 is replaced with its complement. So, if I want to derive JK equations for assignment number 2, I could start from scratch, but I can just look at these equations here and make the transformations here. So for J1 and K1, I'm going to replace 1 with 2 and 2 with 1. So 1 with 2 and 2 with 1 here. And 3 with 3 prime. So I'll put a prime there and take it away here. So my J2 equations then are Q1 prime plus x prime Q3 prime plus x Q3. And for K2, I've got x prime Q1 plus x Q1 prime. And I can transform these equations. Again, I'm replacing flip-flop 2 with flip-flop 1, and 1 with 2, and 3 with 3 prime, and 3 prime with 3. So J1 is xQ3 prime, or x prime Q2 Q3. And K1 will be Q2 or XQ3. Now, for flip-flops 3, here I'm again going to replace 1 with 2 and 2 with 1. But since I have complemented the outputs of the JK flip-flop number 3, when previously I was setting the flip-flop to 1, I now want to set it to 0 and vice versa. So I have to interchange J and K to accomplish that. So this will become K3 and this will become J3. So J3 is x prime or Q2 prime, and K3 is X prime Q2 prime or X Q1. And the equation for Z, I'm going to make a similar transformation. 2 becomes 1, 1 becomes 2, and 3 becomes primed. So the new Z is Q1 Q3 prime or X prime Q2 prime Q1. So we've looked at two equivalent assignments, and we've transformed the flip-flop input equations from one assignment to the other. The equations have essentially the same form for both assignments. They'll take the same number of gates, the same amount of logic. So when we're looking for state assignments, we don't have to try all possible state assignments, because there's no point in trying two equivalent assignments. We only have to try those that are not equivalent. Now, in general, when we're making state assignments, we can choose a good state assignment by applying certain guidelines. So here's an example of a state table, and we're going to make a state assignment here by applying guidelines. The objective of the guidelines is, again, to reduce the amount of logic. So let's look at guideline number 1. Guideline number 1 tells us that states which have the same next state for a given input should be given adjacent assignments. And by adjacent assignments, we mean assignments that differ in only one of the state variables and only one of the flip-flops. So let's look at this table and apply guideline number 1. Which states have the same next state for input x equals 0? Well, here's the next state. A appears in 3 places. And so states A, B, and F all have the same next state. So we should put A, B, and F in adjacent squares on our assignment map. All right. No other pairs in this column. In this column we have D here and D here. So states A and D have the same next state. They should be given adjacent assignments, A and D. And E and F both have next state of E. So E and F should be given adjacent assignments. So that's one guideline. Another guideline, here's the same state table, and we're going to apply guideline 2, which tells us states which are the next states of the same state should be given adjacent assignments. That is, A and D are next states of state A, so they should be given adjacent assignments. A and F are next states of B. They should be given adjacent assignments. B and E are next states of C. They should be adjacent assignments. And here's another BE down here, which are next states of E. So I'm going to put that 2x, because that's more important, because it appears 2 places. D and F are next states of state D. And A and E are next states of F. And then there's a third guideline which will help us simplify the output function. The first 2 guidelines help us simplify the next state function by putting adjacent ones together on the Carnot maps. So this guideline tells us that states which have the same output should be given adjacent assignments. So we're going to look at the output here. Now, all states have an output of 0 here, but that's rather meaningless, so we're not going to even bother with that. But instead, we're going to look at where both outputs are the same for x0, 0, and x equal 1. And here we have 0, 0, 0, 0, 0, 0, 0, 0, corresponding to states A, B, D, and F. So we should give A, B, D, and F all adjacent assignments. And then states C and E have the same outputs for both x equals 0 and x equals 1. So we're going to give C and E adjacent assignments. So in summary, our guidelines give us a number of groups of states which should be given adjacent assignments. Now, the next thing we're going to do is fill in some Karnaugh maps and try and satisfy as many adjacencies as possible. Now, this is a trial and error procedure. There's no algorithm. I can't give you a turn the crank procedure where you can just go ahead and follow that and come up with a good solution. You have to use some reasoning, think about it, and some trial and error. So let's give it a try here. We'll start here with guideline number 1. First of all, the starting state A is usually assigned 0, 0, 0. That's because when we reset our flip-flops, they normally reset to state 0, 0, 0. So I'm always going to put A in this square. And because of the equivalent assignments, I can't do any better by putting A someplace else, because I could always complement or interchange columns and end up with a 0, 0 assignment for A. So I may as well start with A there. And then we have ABF should be adjacent. ABF should be adjacent. ABF adjacent. And then AD. Now AD could go, D could go here, or it could go down here. There's two possibilities, and I probably want to end up trying them both. But let's go ahead and put D here as a first trial. And then E and F. E could go either of two places. E could go here, adjacent to F, or it could go here, adjacent to F. And does it make any difference? It probably doesn't. Let's try putting it here. All right, now how are we doing? Well, if we go to, we've satisfied all of guideline number 1. Guideline number 2, we've got AD. We don't have AF. So we could try swapping things around, maybe improve the situation. We've got A. If we wanted AF too, we could interchange here. So let's put F here and B here. We still have ABF, we still have AD, and we no longer have EF, but we picked up another one. So there is AD, AF, and we picked up BE, and that's important because that's two places. We don't have DF, we don't have AE, we don't have ABDF, and we can satisfy CE by putting C next to E. So that's one possibility, like put C down here. We don't need C adjacent to F, so we may as well put it down here. Now, let's see if we can do better. So let's start out again, and this time I'm going to put A, B, D, F all in one column and try and satisfy ABF and AD and AF and DF if I can do all of those. I don't know. So we just have to try. Start out with A up here, and since we want AF, I'm going to put F here and B here. So I've now got ABF, and I want AD. I'll put AD down here. So I've got ABF satisfied. I've got AD satisfied, and that appears twice, so that's an important one. I've got AF satisfied. Now BE, I can't do both BE and AE, and I'm going to give preference here to BE. because that appears twice. So I'll do BE here. And then what about CE? Again, there's two choices here. It probably doesn't make too much difference. I'll just go ahead and put C adjacent to E here. So let's see how well we did. We satisfied ABF. They're in 3 adjacent squares. We satisfied AD. We did not satisfy EF. We got AD. We got AF. We got BE. We did not get DF. We did not get AE. We got ABDF, and we got CE. So that's all plus except 3. Now, it's not clear that we could do any better if we tried again. We might do that just to see if there's a chance of picking up another guideline, because generally the more guidelines we satisfy, the simpler the logic functions are going to be. So let's try one here with A, B, F in that pattern. And that's not going to work as well because we want A and D is twice. So we want to be sure and pick that up. So I still want to put D adjacent to A here. And to pick up ABF and ABDF, I have to put F here. So that's not, that's a little bit different than we had before. So let's go on with that one. Try BE, and that's important, so I'm going to put E down here, and which means we can't do AE again. And what's left? CE. And so C can go here or here. And let's see, we've satisfied ABF are in adjacent squares, AD, not EF, AD, not AF, BE top to bottom, DF we picked up this time. We don't have AE. We've got AB, DF, and CE. So again, we've missed 3 of the guidelines. So these 2 assignments are probably just about as good. The only way to find out which one is best is to actually derive the next state equations. A convenient way to do that would be using the Logic Aid program. Just plug in the state assignments. So let's pick one of the state assignments here. Let's say I pick this third one here where A is 0, 0, 0. B is 1, 0, 0. C is 0, 1, 0. D is 0, 0, 1. E is 1, 1, 0. F is 1, 0, 1. So I could either use the Carnot maps and derive the flip-flop input equations, or I could use the Logic Aid program. So in general, finding a good state assignment involves some trial and error. We try to satisfy as many guidelines as possible. And then, in order to be sure we get the best assignment, we'd have to try a lot of different assignments and run it through a computer program or through Carnot maps. And in general, we don't have to find the absolute best assignment, but we do want to find a good assignment which reduces the amount of logic required. So we've talked about 2 things which help us simplify logic. First, reducing the state table by finding equivalent states, and then finding a good state assignment.